Hello there, and welcome to Zero Drift, your peaceful passage through the universe. Tonight, we are going to explore one of the most quietly astonishing ideas in the history of physics. An idea that begins with a question so simple it sounds almost childlike: can we keep zooming in forever? And ends in a place where the very concepts of space and distance and reality, as we understand them, dissolve into something that no human instrument has ever seen and no human mind can fully picture. This is the story of the Planck length, the smallest meaningful distance in the universe, the scale at which the laws of physics, as we know them, break down completely, the point at which the act of trying to see something creates a black hole that swallows the very thing you were looking for. The frontier where quantum mechanics and gravity collide and neither emerges intact, and where something new, something we do not yet fully understand, must take their place. It is a story about light and matter and energy and spacetime, about microscopes and particle accelerators and the strange quantum nature of measurement itself, about the Heisenberg uncertainty principle and what happens when you try to extend it to include gravity, about string theory and loop quantum gravity and the possibility that space itself, at the deepest level, is not continuous but granular, made of discrete, indivisible pieces no smaller than the Planck length. And it is a story about limits, about the fact that the universe, for all its vast and open generosity, does have edges, does have places where the questions we can ask run out, does have a smallest scale, a fundamental grain, a point beyond which the word smaller loses its meaning. So settle in, let your body grow heavy and still, let your breathing find its own slow rhythm, and allow the story of the Planck length, of what happens when you try to zoom in forever, to carry you gently towards sleep. To understand the Planck length, we need to begin with something much more familiar. We need to begin with the act of seeing. Sight is so ordinary, so constant, so intimately woven into the fabric of daily experience that we rarely think about what it actually involves at the physical level. We open our eyes and the world appears, colors and shapes and distances and textures, all presented to us with apparent immediacy, as if reality was simply reaching in and painting itself directly on our awareness. But of course, it is not like that. Seeing involves a physical process, and like all physical processes, it has requirements and limitations. To see an object, light must scatter from that object and reach your eye. The light is the messenger. The eye is the detector. And the object is what the light bounces off of on its way to you. This might seem obvious, but it has a consequence that is less obvious. The detail with which you can see an object, the finest feature you can resolve, depends on the wavelength of the light you are using. Wavelength is the spatial scale of the light wave, the distance between successive crests of the electromagnetic oscillation. And there is a fundamental rule: you cannot resolve a feature smaller than the wavelength of the light illuminating it. The reason lies in the wave nature of light. When light waves encounter an object, they interact with it, they scatter, they diffract, they interfere. But if the object is much smaller than the wavelength of the light barely notices it. The waves wash over the object almost as if it were not there, like ocean swells rolling past a small buoy without reflecting significantly. The buoy disturbs the waves a little, but the information about its exact size and shape is lost in the wash. To detect the fine details of the buoy, you would need shorter waves, ripples rather than swells, waves whose scale was comparable to the size of the object you were trying to observe. This is why the finest detail that a conventional optical microscope can resolve is about 200 nanometers, about 1/5 of a millionth of a meter. Visible light has wavelengths in the range of about 400 to 700 nanometers, and no optical instrument, however perfectly made, can resolve features significantly smaller than the wavelength of the light it uses. The physics of waves sets a hard limit that no amount of engineering can overcome. Let your breathing slow now. The world outside is quiet. The story of seeing, of how we probe the small, is just beginning, and it is going to take us from the scale of human hair all the way down to the smallest possible scale in the universe. The history of our ability to see the small is, in essence, a history of using shorter and shorter wavelengths of radiation as probes. Each new generation of instruments has pushed the frontier of resolution by accessing electromagnetic radiation with shorter wavelengths and higher energies. When physicists wanted to see atoms, objects roughly a tenth of a nanometer in size, 1,000 times smaller than what optical microscopes could resolve, they turned to X-rays, which have wavelengths in exactly this range. X-ray crystallography, developed in the early 20th century by William Henry Bragg and his son William Lawrence Bragg, used the diffraction of X-rays from crystalline materials to map the positions of atoms with extraordinary precision. It was X-ray crystallography that revealed the double helical structure of DNA in 1953, in one of the most consequential scientific discoveries in history. But atoms are not the smallest things. Inside atoms are nuclei, tiny, dense cores of protons and neutrons, roughly 100,000 times smaller than the atom itself. To see inside nuclei, to resolve their structure, requires probes with wavelengths 100,000 times shorter than those that can see atoms and correspondingly higher energies. This is where particle accelerators enter the story. A particle accelerator takes charged particles, usually protons or electrons, and accelerates them to very high speeds using electric and magnetic fields, giving them large amounts of kinetic energy. At very high energies, the de Broglie wavelength of a particle, the quantum mechanical wavelength associated with any particle of matter, equal to Planck's constant divided by the particle's momentum, becomes extremely short. Short enough to resolve nuclear structure, short enough to see quarks. The connection between energy and resolving power is the central theme of this story, and it is expressed in a beautifully simple equation. To resolve a feature of size delta x, you need a probe with energy roughly equal to Planck's constant times the speed of light divided by delta x. The smaller the feature you want to resolve, the higher the energy you need. And this relationship is universal. It applies equally to light and to matter, to photons and to electrons and to protons, because at sufficiently high energies, the energy wavelength relationship for all particles converges to the same form. This is one of the great unifying insights of 20th century physics. The distinction between matter and light, between particles and waves, which seems so fundamental at human scales, dissolves at high energies into a single unified relationship between energy and the scale of the phenomenon being probed. To see smaller, use more energy, always. Let us follow the logic of this relationship through the history of particle physics, from the first glimpses of nuclear structure to the frontiers of the Large Hadron Collider at CERN. The first experiments to reveal that protons had internal structure were carried out at the Stanford Linear Accelerator Center, SLAC, in California, beginning in 1967. A team of physicists led by Jerome Friedman, Henry Kendall, and Richard Taylor fired beams of electrons with energies up to about 20 gigaelectron volts at targets of liquid hydrogen and deuterium. At these energies, the de Broglie wavelength of the electrons was comparable to or smaller than the size of the proton, about a femtometer, a millionth of a billionth of a meter, and the electrons could probe the interior of the proton directly. What they found astonished the physics community. The electrons were not scattering smoothly from the proton, as if the proton were a diffuse, uniform blob of charge and matter. They were scattering with large deflections, as if they were bouncing off hard, point-like objects inside the proton. These point-like constituents were the quarks, the fundamental particles that make up protons and neutrons, held together by the strong nuclear force. The SLAC experiments earned Friedman, Kendall, and Taylor the Nobel Prize in Physics in 1990. The discovery of quarks opened a new frontier. The quarks themselves, as far as we can currently tell, have no internal structure. They appear to be point particles, truly fundamental, not made of anything smaller. But is that the final answer? Or are there structures inside the quarks, waiting to be revealed by probes of even shorter wavelength and higher energy? This is where the Large Hadron Collider at CERN enters. The LHC is the largest and most powerful particle accelerator ever built. A ring 27 kilometers in circumference, buried beneath the countryside near Geneva, Switzerland, in which beams of protons are accelerated to nearly the speed of light and collided head-on with energies up to 14 tera-electron-volts. At these energies, the probing wavelength is roughly 10 to the negative 18 meters, a billion times smaller than an atom, 10 times smaller than a proton. The LHC has not found any internal structure in the quarks. They continue to appear point-like at the scales accessible to the most powerful microscope ever built. But it has found something else, something that was predicted by the standard model of particle physics and confirmed by the LHC experiments in 2012. It found the Higgs boson, the quantum excitation of the Higgs field that permeates all of space and gives mass to the fundamental particles. The Higgs boson discovery was one of the great triumphs of modern physics, confirming the last missing piece of the standard model. But it also, in a sense, completed the standard model rather than overturning it. The question of what lies beyond, of whether there are structures smaller than quarks, of what new physics might emerge at energies higher than the LHC can reach, remains open. And it is here that the story takes its most dramatic turn. Drift deeper now, as the night holds you and the story approaches its most remarkable destination. We have been following the logic of resolution, the idea that to see smaller, you need higher energy probes. We have seen this logic validated at every scale, from atoms to nuclei to quarks, each new generation of instruments revealing new structure by using higher energy and shorter wavelength probes. But what happens if we keep going? What happens if we keep increasing the energy of our probes, pushing to smaller and smaller scales, following the logic of resolution to its ultimate conclusion? Something extraordinary happens, something that the logic of resolution, followed to its limit, generates out of itself. Something that is simultaneously a prediction of Einstein's general relativity and a consequence of quantum mechanics. Something that suggests, with the force of mathematical necessity, that there is a smallest possible length in nature, a scale below which the very concept of distance loses meaning. Let us follow the argument. Einstein's general theory of relativity tells us that energy curves spacetime. Mass and energy are equivalent, and wherever mass and energy are present, they bend the fabric of space and time around them. This is gravity, in Einstein's understanding, not a force acting across empty space, but the curvature of spacetime itself, produced by the distribution of mass and energy and felt by everything moving through that curved spacetime. Now, as we focus higher and higher energy into a smaller and smaller region of space, as we push our probe to shorter wavelengths and higher energies, the energy density in the probed region increases. And as the energy density increases, the curvature of spacetime in that region increases. Spacetime bends more and more sharply around the concentrated energy. At some point, and this is the key insight, the energy density becomes so extreme that the spacetime curvature in that region becomes self-reinforcing. The region cannot support itself against its own gravity. It collapses, a black hole forms, and a black hole is the ultimate hiding place. Once something falls inside a black hole, once it crosses the event horizon, the boundary within which the escape velocity exceeds the speed of light, it is gone. No information about it can escape to the outside universe. The region we were trying to observe has been swallowed by its own gravity, hidden behind an event horizon from which not even light can escape. In other words, the very act of trying to see what is happening at very small scales causes a black hole to form at those scales, hiding the very thing we were trying to see. The tool of observation has become an instrument of concealment. The more energy we pour in to sharpen our view, the bigger the black hole we create, and the more completely the region we were trying to observe is hidden from us. This is not a technological limitation. It is not something that better engineering could overcome. It is a fundamental consequence of the laws of physics as we currently understand them. General relativity says that concentrated energy creates black holes. Quantum mechanics says that resolving small scales requires concentrated energy. Together, they imply that there is a smallest scale below which resolution is impossible in principle. That scale is the Planck length. Planck length emerges from the interplay of three fundamental constants of nature: Newton's gravitational constant g, which sets the strength of gravity; Planck's constant h, which sets the scale of quantum mechanical effects; and the speed of light c, which connects space and time in Einstein's relativity. The Planck length is proportional to the square root of g times h divided by c cubed. Its value is approximately 1.6 times 10 to the negative 35 meters. Written out in full, it is a decimal point followed by 34 zeros, and then the digits 16, an almost incomprehensibly small number. To appreciate how small this is, consider the following comparisons. A proton is roughly 10 to the negative 15 meters in size, a femtometer. An atom is roughly 10 to the negative 10 meters, an angstrom. A bacterium is roughly 10 to the negative 6 meters. A grain of sand is roughly 10 to the negative 4 meters. A human being is roughly 1 to 2 meters. The Earth is roughly 10 to the 7 meters in diameter. The observable universe is roughly 10 to the 26 meters across. The Planck length, at 10 to the negative 35 meters, is 20 orders of magnitude smaller than a proton. To put that in perspective, the ratio of the Planck length to a proton is roughly the same as the ratio of a proton to something about 1 billion times the size of the observable universe. The Planck length is not just small. It is small in a way that exhausts our capacity to form intuitions about scale. And yet it emerges, cleanly and inevitably, from three constants that we know from experiment, connected by the logic of combining gravity and quantum mechanics. The Planck length is not an arbitrary choice or a convention or a guess. It is the natural scale set by the combination of gravitational, quantum mechanical, and relativistic effects, the scale at which all three become equally important simultaneously. As you rest in the quiet of this night, let the Planck length be a kind of anchor for your thoughts, not something to grasp tightly, but something to hold lightly, a number that points toward the deepest layer of physical reality that we have so far been able to identify. There is a second path to the Planck length, an entirely different line of argument that arrives at the same conclusion by a completely different route. This path runs through the Heisenberg uncertainty principle, the foundational result of quantum mechanics that sets limits on how precisely we can simultaneously know certain pairs of physical quantities. The Heisenberg uncertainty principle, in its most familiar form, states that the uncertainty in the position of a particle and the uncertainty in its momentum cannot both be made arbitrarily small simultaneously. The more precisely you know where a particle is, the less precisely you can know how fast it is moving, and vice versa. This is not a limitation of our instruments. It is a fundamental feature of quantum reality. The principle emerges naturally from the wave nature of quantum particles. To locate a particle precisely in space, you need a wave with a very short wavelength, because the particle's position is related to the spatial structure of its wave function, and fine spatial structure requires short wavelengths. But short wavelengths correspond to large momenta, because the momentum of a quantum particle is inversely proportional to its wavelength, and a large momentum means a large uncertainty in momentum. The two quantities, position and momentum, are linked in this way, and the uncertainty principle quantifies exactly how tightly they are linked. Now, the Heisenberg uncertainty principle, in its standard form, is a result of quantum mechanics alone. It does not include gravity. But what happens when we extend it to include the gravitational effect of the probe we are using to make the measurement? Consider trying to measure the position of an electron with high precision. We do this by scattering a photon off the electron and observing where the photon goes after the collision. To achieve high positional precision, we need a photon with a short wavelength, which means a high-energy, high-momentum photon. But a high-energy photon carries energy, and energy is equivalent to mass. This mass, however small, produces a gravitational field. As the high-energy photon approaches the electron, its gravitational field exerts a tiny pull on the electron. This gravitational pull displaces the electron slightly, adding an additional uncertainty to the electron's position beyond what the standard Heisenberg principle predicts. And as we make the photon more energetic to sharpen the position measurement, the gravitational displacement grows. We are caught in a bind, increasing the photon's momentum to reduce one source of position uncertainty increases another source through gravity. When we carry through the calculation, working out the size of the gravitational displacement of the electron due to the photon's gravitational field, and combining this with the standard Heisenberg uncertainty, we arrive at what is called the generalized uncertainty principle. This modified uncertainty principle has two terms. The first is the standard Heisenberg term, which becomes smaller as the probing momentum increases. The second is a gravitational term, which becomes larger as the probing momentum increases. The sum of these two terms has a minimum, a smallest possible value of the position uncertainty, below which no measurement can go, no matter how much energy you pour into the probe. And when you calculate this minimum, it comes out to be, once again, the Planck length. The same conclusion, reached from a completely different direction, from the logic of black hole formation, from the logic of gravitational corrections to the uncertainty principle. Two independent arguments, two different physical insights, the same fundamental answer. Nature sets a minimum length. Below the Planck length, the concept of position, of spatial location, loses operational meaning. Distance at that scale is not merely difficult to measure, it is not merely beyond current technology, it is undefined. There is no fact of the matter about whether one Planck length scale region of space is at this location or that one. The smooth, continuous spacetime that underlies all of classical physics and all of quantum mechanics as currently formulated gives way to something we do not yet have the tools to describe. Let your eyelids grow heavier as the story moves into the territory of the unknown, the frontier where our best theories break down and something new must take their place. The Planck length is not merely a scale at which calculations become difficult. It is a scale at which the theoretical frameworks that underlie all of modern physics cease to be valid. Both quantum mechanics and general relativity, as they are currently formulated, assume that spacetime is a smooth, continuous manifold, a mathematical structure in which distances can be defined with arbitrary precision. Quantum mechanics uses this smooth spacetime as the background against which quantum fields propagate and quantum states evolve. General relativity describes how this smooth spacetime curves in response to matter and energy. But at the Planck scale, this smoothness cannot be maintained. The quantum fluctuations of spacetime itself, the unavoidable quantum uncertainty in the gravitational field, in the curvature of space and time, become of order 1. Spacetime at the Planck scale is not smooth. It is, in some sense we do not yet fully understand, wildly fluctuating, indefinitely curved, granular, the spacetime foam that the physicist John Wheeler described as the fundamental texture of space at the smallest scales. In this regime, the classical notion of distance, the idea that you can ask how far apart two points in space are and get a well-defined answer, breaks down. The quantum uncertainties in the positions of those points are comparable to the Planck length itself. There is no meaningful sense in which you can distinguish between 2 points separated by less than the Planck length. This is what the physicist Nima Arkani-Hamed meant when he said that spacetime, at the Planck scale, emerges as an approximate notion, a large-scale description that emerges from some deeper structure we do not yet understand, valid at the scales we can observe but breaking down at the Planck scale. What is that deeper structure? This is the central question of quantum gravity, and it is one of the deepest unsolved problems in all of physics. Two of the most developed approaches to quantum gravity are string theory and loop quantum gravity, and they take very different approaches to the problem of what happens at and below the Planck scale. String theory begins from the observation that the fundamental building blocks of nature, rather than being point particles with no size, are tiny one-dimensional objects, strings, with a characteristic length comparable to the Planck length. These strings can vibrate in different ways, and the different vibrational modes of the string correspond to different fundamental particles. A string vibrating in one mode appears as an electron. A string vibrating in another mode appears as a photon. A string vibrating in yet another mode appears as a graviton, the quantum particle of the gravitational field. The key feature of string theory for our story is that the finite size of the strings builds in a natural resolution limit. When you try to probe a string at very high energy, rather than revealing smaller and smaller structure within the string, you instead excite more and more vibrational modes of the string. The string becomes more extended, not more tightly localized. The effective size of the probe grows rather than shrinks. This means that string theory automatically incorporates the kind of minimum length scale that we derived from the black hole and uncertainty principle arguments. In string theory, you cannot probe distances smaller than the string length, not because a black hole forms and not because the uncertainty principle prevents it, but because the string itself spreads out in response to the high-energy probing. The minimum length is built into the fundamental description of matter, rather than being an emergent consequence of combining two existing theories. Remarkably, string theory, which begins as a quantum theory of vibrating strings, automatically generates Einstein's general relativity as a large-scale consequence. Gravity is not something added to string theory by hand. It emerges from the strings themselves. The graviton, the quantum of the gravitational field, appears naturally in the string spectrum as one of the vibrational modes of the closed string. In this sense, string theory unifies quantum mechanics and gravity not by modifying either, but by finding a deeper description from which both emerge. String theory also generates its own version of the generalized uncertainty principle, a modified uncertainty relation that looks strikingly similar to the one we derived from quantum mechanics and gravity, with a minimum length of order the string length. This convergence between results derived from quantum gravity arguments and results derived from string theory is one of the most intriguing hints that string theory is on the right track, even though direct experimental confirmation remains far out of reach. Loop quantum gravity takes a different approach. Rather than introducing new fundamental objects, strings, and asking what emerges from them, loop quantum gravity takes seriously the idea that spacetime itself must be quantized. In general relativity, spacetime is a smooth, continuous entity, the metric field that encodes all the geometric properties of space and time. In loop quantum gravity, this smooth field is replaced by a quantum object, a network of discrete, quantized states called spin networks. In a spin network, space is not a continuous backdrop, but a collection of discrete quanta of volume, connected by discrete quanta of area. The links between nodes in the network represent areas, and the nodes themselves represent volumes. Space, in this picture, is fundamentally granular, made of indivisible pieces, like a mosaic made of tiles, with the tiles having a characteristic size of order, the Planck length. In loop quantum gravity, the question of what happens below the Planck length does not arise, because there is no below. Space is not infinitely divisible in loop quantum gravity. It has a minimum quantum of volume, a smallest possible chunk of Planck scale size. The geometry of space is discrete, and the discreteness is built in at the fundamental level of the theory. The Big Bang, in the loop quantum gravity framework, is replaced by a big bounce, a minimum volume state in which the universe did not begin in a true singularity of infinite density, but in a state of maximum quantum density, from which it then expanded. The singularity theorems of general relativity, which predict that the geometry of spacetime breaks down at the centers of black holes and at the Big Bang, are resolved in loop quantum gravity because the discrete quantum geometry cannot be compressed below the Planck scale. Both string theory and loop quantum gravity are active research programs with genuine successes and genuine open problems. Neither has yet made a prediction that can be tested with current or near-future experiments. The Planck scale, the scale at which quantum gravitational effects become important, is so far beyond the reach of any conceivable particle accelerator that direct experimental probes of Planck-scale physics seem, at present, far out of reach. But there are indirect approaches. Astronomical observations of the cosmic microwave background, of gravitational waves from the early universe, of high-energy cosmic rays, might carry faint imprints of Planck-scale physics. The mathematics of string theory has generated deep connections to other areas of physics and mathematics, some of which have been tested indirectly. And the conceptual insights from both approaches have already transformed our thinking about the nature of spacetime, the origins of the universe, and the relationship between quantum mechanics and gravity. The night is deep around you now, and the story has reached the frontier of what is known. We began with the act of seeing, with the simple fact that to observe something, you need to scatter radiation from it, and the detail you can see depends on the wavelength you use. We followed the logic of resolution from visible light to X-rays to electron beams to particle accelerators, watching the energy increase and the probing scale decrease at every step. We saw how this logic has driven the history of particle physics, from the discovery of atomic structure to the discovery of nuclear structure, to the discovery of quarks, to the discovery of the Higgs boson. And then we followed the logic one step further, to the scale where the energy concentrated in the probe becomes so large that gravity can no longer be ignored, where the curved spacetime produced by that concentrated energy creates a black hole, where the very act of probing the small creates an impenetrable barrier to further observation. We saw that this scale, the Planck length, emerges from the combination of Newton's gravitational constant, Planck's quantum of action, and the speed of light, three constants from three different fundamental theories, combined in the unique way that produces a length. And we saw that the same scale emerges from an entirely different argument, from the generalized uncertainty principle, which combines the standard Heisenberg uncertainty with the gravitational displacement caused by the probe, and finds a minimum possible uncertainty in position of Planck scale size. Two arguments, two perspectives, one answer. Nature has a minimum length. Below the Planck scale, space, as we currently understand it, ceases to exist in any operationally meaningful sense. What exists below the Planck scale, what the true nature of spacetime is at the most fundamental level, is the great open question of contemporary theoretical physics. String theory offers one answer. Loop quantum gravity offers another. Other approaches, including causal dynamical triangulation and asymptotic safety, offer others still. None has yet produced a definitive experimental prediction that would allow us to choose between them, but all of them agree on one thing. The smooth, continuous spacetime of classical physics and of quantum field theory, as currently formulated, is not the final story. It is an approximation, a large-scale description that emerges from some deeper, more fundamental structure at the Planck scale. That deeper structure is what we are seeking, and the search for it is one of the most profound intellectual adventures that our species has ever undertaken. The energy required to probe the Planck length directly with a particle accelerator is the Planck energy, approximately 10 to the 19th giga-electron volts. The Large Hadron Collider reaches about 14 tera-electron volts, 14,000 giga-electron-volts. The Planck energy is about 1,000,000 billion times higher. To build a particle accelerator capable of reaching the Planck energy, using the same technology as the LHC but simply scaled up, you would need a machine with a circumference of roughly 4,000 light-years, hundreds of times larger than our solar system, and a few percent of the size of our entire galaxy. This is not a near-future engineering challenge. It is not even a far-future engineering challenge in any recognizable sense. It is beyond the scale of anything that our civilization, or any civilization we can plausibly imagine, could build in any conceivable future. The Planck scale is not just very small. It is operationally inaccessible by any direct means currently known. But here is what is remarkable. We know the Planck length exists. We know it is the fundamental scale of quantum gravity. We know its value to many significant figures. And we know all of this not because we have probed it directly. We have not, and may never be able to, but because the logic of combining our best theories leads there inevitably. The Planck length is a theoretical construct, but one of extraordinary robustness, emerging from two completely independent lines of reasoning, from the physics of black holes and from the physics of quantum measurement, and confirmed as the natural scale where all three fundamental constants of nature are simultaneously relevant. It is humbling to contemplate. We have built the most powerful microscope in human history, the Large Hadron Collider, and used it to probe matter at scales 20 orders of magnitude smaller than an atom. And the Planck length is 20 orders of magnitude smaller still. We are, in terms of our experimental reach, as far from the Planck scale as the LHC is from the human eye. The frontier is real, but it is extraordinarily distant. And yet the frontier matters, not because we expect to probe it directly in the near future, but because it tells us something profound about the nature of physical reality, that the smooth, continuous spacetime we experience at human scales is not the fundamental structure of the universe. That at the deepest level, space and time may be granular, discrete, built from indivisible pieces of Planck-scale size. That the concept of distance, which seems so immediate and so fundamental to our experience of the world, is not ultimately fundamental at all. It is emergent, arising from something deeper that we have not yet fully understood. Let the quiet of this hour carry you gently. The story has moved from the act of seeing to the limit of seeing, from the simplest optical microscope to the edge of what is knowable. And in that journey, something has been revealed about the nature of the universe that is, in its way, deeply comforting. The universe has laws. It has a structure. That structure has a scale, the Planck length, below which our current descriptions break down, but above which they work with extraordinary precision and extraordinary generality. The fact that the same scale emerges from two completely different lines of reasoning is a sign that we are touching something real, that the Planck length is not an artifact of our current theoretical framework, but a genuine feature of physical reality, something that any correct theory of quantum gravity must incorporate and explain. And the search for that theory, the search for the description of spacetime at and below the Planck scale, is one of the most ambitious and most beautiful intellectual projects in the history of science. It is ambitious because the scale is so far beyond direct experimental reach. It is beautiful because the question it asks is so fundamental. What is space? What is time? What is the fabric of reality made of at the most basic level? And because the partial answers we have found already, from string theory and loop quantum gravity and the generalized uncertainty principle, are so rich and so suggestive, we do not yet know the answer, but we know the question. And knowing the question, knowing that there is a minimum length, a fundamental scale, a grain to the fabric of spacetime, is itself a remarkable achievement. It tells us that the universe, for all its openness and all its generosity of detail, is not infinitely deep. It has a bottom. It has a most fundamental level. And we are, for the first time in the history of our species, close enough to that level to see its outline, even if we cannot yet see its face. The story of how physicists came to understand the relationship between energy and resolution is inseparable from the story of quantum mechanics itself, the revolution in our understanding of nature that unfolded in the 1920s and transformed physics forever. At the beginning of the 20th century, the atomic theory of matter was still not universally accepted. The idea that matter was made of discrete, indivisible atoms rather than a continuous fluid was compelling in its explanatory power. It explained the laws of chemistry, the behavior of gases, the diffusion of substances, but it lacked direct experimental confirmation. Atoms were too small to see with any instrument then available, and some serious scientists regarded them as a useful fiction rather than a physical reality. The situation changed dramatically in 1905 when Albert Einstein published 4 papers of extraordinary importance. One of them on Brownian motion, the random jiggling of tiny particles suspended in a liquid, driven by the invisible thermal buffeting of water molecules, provided the first quantitative, testable evidence for the existence of atoms. By calculating the statistical properties of Brownian motion from the atomic theory and comparing them with the observations of the botanist Robert Brown, Einstein demonstrated that the atomic theory made precise and correct predictions. Within a few years, the experimental confirmation of these predictions by Jean-Baptiste Perrin settled the question definitively. Atoms were real. Another of Einstein's 1905 papers explained the photoelectric effect, the emission of electrons from a metal surface when light of sufficiently high frequency falls upon it, by proposing that light was not a continuous wave, but a stream of discrete energy packets, each carrying energy proportional to the frequency of the light. These packets, later named photons by the physicist Gilbert Lewis, were the first quanta of radiation, and Einstein's explanation of the photoelectric effect was the first successful application of the quantum hypothesis to the electromagnetic field. The quantum hypothesis had been introduced 5 years earlier by Max Planck, who had used it to resolve the ultraviolet catastrophe, the catastrophic failure of classical physics to correctly predict the spectrum of light emitted by hot objects. Planck showed that the experimental observations could be explained if energy was transferred between matter and radiation in discrete packets rather than continuously, and he derived the constant that bears his name, Planck's constant, as the proportionality factor between the frequency of radiation and the size of the energy packet. Planck himself was not entirely comfortable with the quantum hypothesis and hoped for years that it would prove to be a mathematical device rather than a physical reality. Einstein had no such reservations. He embraced the quantum hypothesis and showed that it applied not just to the emission and absorption of radiation, but to the radiation field itself, that light was fundamentally quantum in nature. This insight, combined with Louis de Broglie's later proposal that matter had wave-like properties, that electrons and protons and other particles had associated wavelengths inversely proportional to their momenta, laid the foundation for quantum mechanics. The wave nature of matter was confirmed in 1927 by Clinton Davison and Lester Germer, who observed the diffraction of electrons from a nickel crystal in exactly the way de Broglie's theory predicted. The same year, Werner Heisenberg formulated the uncertainty principle, showing that the wave-particle duality of quantum mechanics implied fundamental limits on the simultaneous precision of position and momentum measurements. All of this, Planck's constant, the photoelectric effect, de Broglie's matter waves, the Heisenberg uncertainty principle, is woven into the story of the Planck length. The Planck length is literally made of Planck's constant, combined with Newton's gravitational constant and the speed of light. It is a convergence point of 3 theories, quantum mechanics, gravity, and relativity, each of which contributed one of the 3 constants that define it. There is a thought experiment that illustrates the impossibility of probing below the Planck length with particular clarity, and it is worth dwelling on because it reveals the deep logic of the situation without any mathematics. Imagine that you are trying to photograph something extraordinarily tiny. You have a camera, a very special camera, that can use any kind of radiation you like, with any energy you like. You can use visible light, or X-rays, or gamma rays, or high-energy electrons, or even protons. Whatever you use, the rule is the same. Finer detail requires shorter wavelength. Shorter wavelength requires higher energy. You start with visible light and photograph a cell. Then you use X-rays and see individual molecules. Then you use electron beams and see individual atoms. Each time you increase the energy, you see smaller structures. You continue up through the energies reached by successive generations of particle accelerators, seeing quarks and gluons and the structure of the proton. The universe keeps revealing finer and finer details as you pour in more and more energy. Now you decide to push further. You want to see what, if anything, exists at scales smaller than anything ever observed, smaller than quarks, smaller than the scale probed by the LHC. You increase the energy of your probe dramatically, focusing it into a smaller and smaller region of space. But as you do, something strange begins to happen. The energy you are concentrating into this tiny region has mass by E equals mc squared, and mass creates gravity. As the energy density grows, the gravitational field it creates grows with it. The region of space you are trying to observe begins to curve under the weight of your probe. You push further. The energy density grows. The gravitational curvature grows, and then, at a critical energy, the Planck energy, something catastrophic happens. The gravitational curvature of the probed region exceeds the critical value at which spacetime can no longer sustain itself. The region collapses into a black hole. And a black hole, by definition, hides everything inside it. The region you were trying to photograph is now behind an event horizon. Your photograph is blank. Not because the camera failed, not because the exposure was too short, not because you used the wrong kind of radiation, but because the act of taking the photograph destroyed the very thing you were photographing. If you increase the energy further, trying to overwhelm the black hole with more energetic radiation, you simply make the black hole bigger. The event horizon expands, more of space is hidden, your photograph gets blanker, not sharper. This is the fundamental limit. Below the Planck length, you cannot photograph the universe. Not with any technology, not with any cleverness, not by any means that physics currently knows about. The universe has a smallest scale, and it hides itself there. The Planck energy, the energy at which this catastrophic concealment occurs, is about 10 to the 19th gigaelectron volts. The LHC reaches about 14 teraelectron volts, 14,000 gigaelectron volts. The ratio is roughly 10 to the 15th, 1,000 trillion. The gap between the highest energy we have ever achieved experimentally and the Planck energy is an enormous factor. And the gap in accelerator size scales linearly with the energy gap, which means a Planck energy accelerator built on LHC technology would need to be roughly 10 to the 15th times larger than the LHC in circumference. The LHC's circumference is 27 kilometers. 10 to the 15th times 27 kilometers is about 4,000 light-years. Our galaxy is roughly 100,000 light-years across, so a Planck energy accelerator would be a few % of the size of the entire Milky Way. This is a number that should induce a kind of peaceful awe, not despair. It does not follow that we can never learn anything about Planck-scale physics. There are indirect approaches, and the universe itself may provide natural experiments in the form of cosmic rays, gravitational wave observations, and the imprints of Planck-scale physics on the cosmic microwave background. But it does suggest that the Planck scale is genuinely fundamental in a way that goes beyond mere technological limitation. It is a natural boundary set by the physics of the universe itself, beyond which direct observation becomes meaningless. This is what makes the Planck length philosophically as well as scientifically significant. It is not merely the current limit of our experimental reach, the scale beyond which our instruments are not yet powerful enough. It is the absolute limit of what spatial resolution can mean, the scale below which the concept of distance itself loses operational meaning. The connection between the Planck length and black holes deserves a little more attention because it reveals something deep about the relationship between gravity and quantum mechanics that goes beyond the simple argument we traced earlier. A black hole is characterized in general relativity by the Schwarzschild radius, named for the German physicist Karl Schwarzschild, who derived the exact solution to Einstein's field equations for a spherically symmetric mass less than a month after Einstein published the general theory of relativity in November 1915. Schwarzschild did this remarkable work while serving on the Russian front in the First World War and died just months later from a disease contracted at the front. His solution has become one of the most important in the history of physics. The Schwarzschild radius of an object of mass m is proportional to the gravitational constant g times the mass m, divided by the speed of light squared. If you compress an object within its own Schwarzschild radius, it becomes a black hole. Nothing, not even light, can escape from within that radius. The event horizon is at the Schwarzschild radius. Now, a quantum particle of momentum p has a de Broglie wavelength of Planck's constant divided by p. The energy of an ultra-relativistic particle with this momentum is approximately p times c, momentum times the speed of light. The Schwarzschild radius of this amount of energy, treating the energy as equivalent to a mass via E equals mc squared and calculating the Schwarzschild radius for that mass, is proportional to g times the energy divided by c to the fourth power. At the Planck scale, the de Broglie wavelength of the particle and the Schwarzschild radius of its energy become equal. This is the precise statement of when the black hole forms, when the probe's quantum mechanical extent and its gravitational extent are the same size, when the uncertainty in position imposed by the quantum nature of the probe equals the size of the black hole it would create. This coincidence, de Broglie wavelength equals Schwarzschild radius, occurs at exactly the Planck length. At smaller scales, the Schwarzschild radius would exceed the de Broglie wavelength, meaning that the probe's gravitational collapse would occur before you could localize it at all. The probe would disappear into its own black hole before it could interact with anything. This is the clearest possible statement of why the Planck length is fundamental. It is not just the scale at which gravity becomes important. It is the scale at which the quantum nature of the probe and the gravitational collapse of the probe happen at the same size. Below this scale, the two processes cannot be separated. Quantum mechanics and gravity are inextricably entangled, and neither can be treated without the other. This is why a theory of quantum gravity is needed, not as a matter of aesthetic preference or theoretical completeness, but as a practical necessity for describing what happens at and below the Planck scale. Our current theories, quantum mechanics and general relativity, are both extraordinarily accurate in their respective domains, but those domains do not overlap at the Planck scale. Both must be applied simultaneously, and when you try to apply them simultaneously with the tools currently available, they give inconsistent results. Something new is needed, something that contains both theories as limiting cases but goes beyond both to describe the Planck scale regime. That something is what physicists are searching for when they work on string theory and loop quantum gravity and other approaches to quantum gravity. The search is not abstract or academic. It is aimed at the most fundamental question that physics can ask. What is the fabric of reality made of at the deepest level? What is spacetime at scales a million billion times smaller than anything we have ever observed? We do not yet know, but we know the question. And knowing the question, clearly and precisely, is itself a profound achievement, one that required 2 centuries of physics, from Newton to Maxwell, to Planck to Einstein to Heisenberg, to the builders of the LHC, each generation extending the reach of human, understanding a little further into the unknown. There is a quality to the deepest questions in physics, a quality that the Planck length question has in full measure, that is worth naming before the story rests. It is the quality of pointing beyond themselves. The answer to one deep question always reveals a deeper question behind it. The discovery of atoms raised the question of atomic structure. The discovery of nuclear structure raised the question of quark structure. The discovery that quarks appear point-like raised the question of what happens below the quark scale. And the discovery that below the Planck scale the question itself becomes meaningless raises the question of what replaces it. What kind of description is valid at and below the Planck scale, where spacetime as we know it dissolves? This recursive quality, each answer revealing a deeper question, is not a failure of science. It is science working as it should. Each layer of understanding is built on the layer before it, and each layer reveals the limitations of the previous one in a way that points toward the next. We would not know about the Planck length if we had not understood quantum mechanics and general relativity. We would not have understood general relativity without special relativity. We would not have understood special relativity without the electromagnetism of Maxwell. We would not have understood Maxwell without the mechanics of Newton. The edifice is built layer by layer, each generation inheriting the tools and the knowledge of the previous one and using them to reach a little further. And the Planck length, at the current frontier, is not a wall, it is a signpost. It points toward the next layer, the layer we do not yet have, the layer of quantum gravity, of fundamental spacetime structure, of whatever it is that space and time emerge from at the deepest level. The search for that layer is ongoing. It is the work of theoretical physicists working with mathematics, of observational astronomers looking for indirect signatures of Planck-scale physics in the cosmic microwave background and in gravitational waves, of philosophers of physics examining the conceptual foundations of our current theories. It is one of the great collaborative intellectual adventures of our time. And tonight, lying still and breathing slowly, you are connected to that adventure, not as a participant necessarily, but as a member of the species that asks these questions, that has always asked these questions, that will continue to ask them until the answers are found or until something better than answers is discovered. The Planck length is the current edge of the map. Beyond it there be dragons or strings or spin networks or something we have not yet imagined, but the map is being drawn, the frontier is being approached, and the universe, patient and ancient and deep, is waiting to be understood. The history of particle physics in the 20th century is, in one sense, the history of building ever larger and more powerful accelerators to probe ever smaller scales. Each machine was, in its time, the most powerful microscope ever constructed, and each revealed structure that the previous machine could not see. The first particle accelerator, in the modern sense, was built by John Cockcroft and Ernest Walton at the Cavendish Laboratory in Cambridge in 1932. It accelerated protons to about 700 kilo-electron-volts and used them to split lithium nuclei, the first artificial nuclear reaction. The machine was modest in scale, fitting on a laboratory bench, and the energies it reached were far below those needed to probe nuclear structure directly, but it established the principle. Ernest Lawrence at Berkeley developed the cyclotron, a machine in which particles were accelerated in a spiral path by alternating electric fields and a constant magnetic field, and progressively larger cyclotrons were built through the 1930s, reaching energies of tens of mega-electron volts. After the Second World War, a new type of accelerator, the synchrotron, in which a ring of magnets kept the particles in a circular orbit while they were accelerated, enabled the construction of machines reaching billions of electron volts. The cosmotron at Brookhaven National Laboratory, completed in 1952, reached 3 giga-electron volts. The bevatron at Berkeley, completed in 1954 and reaching 6.2 giga-electron volts, enabled the discovery of the antiproton in 1955. The alternating gradient synchrotrons at Brookhaven and CERN in the late 1950s pushed to tens of giga-electron volts, enabling the detailed study of hadron physics. Through the 60s and 70s, machines at Fermilab in Illinois and CERN in Switzerland pushed into the hundreds of giga-electron volts, then into the tera-electron volt range. The Tevatron at Fermilab, reaching nearly 2 tera-electron volts in proton-antiproton collisions, discovered the top quark in 1995, the sixth and final quark of the Standard Model, the heaviest fundamental particle yet discovered, with a mass comparable to an atom of gold. And then the LHC, the culmination of this progression, reaching 14 tera-electron volts in proton-proton collisions, and discovering the Higgs boson in 2012. Each step in this progression extended the reach of human observation into smaller and smaller scales, revealing new structure, new particles, new forces, new layers of organization in the fabric of matter. The progression has been remarkable not just for the physics it has revealed, but for what it has not revealed. At every scale below the atom, physicists have expected to find new structure, and they have found it repeatedly. Atoms have nuclei. Nuclei have protons and neutrons. Protons and neutrons have quarks. But quarks, so far as we can tell, have no further structure. They appear to be truly fundamental point particles, or at least particles whose size is too small to be resolved by the most powerful accelerator ever built. Is this the end of the layers? Are quarks, along with electrons and neutrinos, and the other fundamental fermions of the Standard Model, truly the most fundamental constituents of matter? Or is there structure below the quark scale, waiting to be revealed by accelerators we have not yet built? We do not know. What we do know is that whatever structure might exist below the quark scale must be at scales smaller than about 10 to the negative 18 meters, the current resolution limit of the LHC. And the scale at which probing directly becomes impossible, the Planck length, is about 10 to the negative 35 meters, 17 orders of magnitude smaller still. Between the current frontier and the Planck frontier, there is an enormous range of scales about which we know essentially nothing. The desert, some physicists call it, a vast expanse of scale where perhaps nothing new exists, and the Standard Model particles and their interactions are all there is until you reach the Planck scale. Or perhaps a jungle teeming with new physics at every scale, waiting to be discovered by more powerful machines. The next generation of particle accelerators, the proposed Future Circular Collider at CERN, or the International Linear Collider in Japan, would extend the reach by modest factors compared to the LHC, perhaps probing scales a few times smaller. But the Planck scale is 17 orders of magnitude away. The gap is vast, and there is no clear path across it in terms of direct accelerator-based experiments. The hope for progress lies partly in indirect approaches, in astronomical observations, in theoretical insights, in the mathematical structures of the candidate quantum gravity theories, and partly in the recognition that the history of physics has repeatedly surprised us. Each time a desert seemed to stretch ahead, an oasis of new physics was found. Each time the current frontier seemed final, a new frontier appeared beyond it. Perhaps the Planck scale will be different. Perhaps it truly is the final frontier, the deepest level, the most fundamental lay. Or perhaps, when we understand quantum gravity well enough to know what questions to ask, we will find that the Planck scale is itself an approximation, that there is something beyond, something our current frameworks cannot even formulate questions about. The history of science does not encourage betting on the finality of any framework. Among the most beautiful and most unsettling aspects of the Planck length is what it implies about the nature of time. We have focused mostly on the Planck length as a spatial scale, a minimum meaningful distance. But the same logic that applies to space applies equally to time, and there is a corresponding Planck time, the time it takes light to travel one Planck length, which is approximately 5 times 10 to the negative 44 seconds. The Planck time is the smallest meaningful time interval, in the same sense that the Planck length is the smallest meaningful spatial distance. Below the Planck time, the concept of temporal sequence, of one event happening before another loses operational meaning. Time, like space, is granular at the Planck scale. The smooth flow of time that we experience, the sense of moments succeeding one another in an unbroken stream, is, at the deepest level, an approximation. Time is not a continuous river, but a succession of discrete steps, each of Planck duration. The Planck time sets an absolute limit on the rate at which physical processes can occur. No physical process can happen faster than the Planck time. Not because of technological limitations, not because of practical constraints, but because there is no such thing as a time interval shorter than the Planck time. The concept of speed requires dividing distance by time, and if neither distance nor time can be subdivided below their respective Planck values, there is a maximum speed, the speed of light, that no process can exceed, for reasons that go deeper than special relativity alone. In the very earliest moments of the universe, in the first Planck time after the Big Bang, the universe was smaller than the Planck length and hotter than the Planck temperature. At this moment, our current physical theories, both quantum mechanics and general relativity, are completely inadequate. The initial conditions of the universe, the question of what happened before the Planck time, if that question even makes sense, cannot be answered with the tools we currently have. This is the deepest mystery in all of cosmology. We can trace the history of the universe with extraordinary confidence and precision back to about 1 second after the Big Bang, when the universe was a hot plasma of protons, neutrons, electrons, and photons. We can trace it back to about 10 to the negative 10 seconds, when the Higgs field acquired its current value and the electroweak symmetry was broken. We can trace it, with less confidence, back to about 10 to the negative 35 seconds, when inflation, a period of exponential expansion, may have occurred. But we cannot trace it back to the Planck time, 10 to the negative 44 seconds, because our theories break down there. The singularity, the point of zero size and infinite density that classical general relativity predicts at the beginning of the universe, is replaced, in quantum gravity theories, by a Planck-scale quantum state from which the universe expanded. But what that state was, and what determined the initial conditions of the universe, is beyond the reach of our current understanding. This is both deeply humbling and deeply exciting. Humbling because the origin of the universe, the most fundamental question about our existence, is precisely in the regime where our theories break down. Exciting because any theory of quantum gravity that successfully describes the Planck scale will also, necessarily, say something about the initial conditions of the universe. The physics of the smallest possible scale and the physics of the origin of everything are the same physics. As the night deepens and the story approaches its final rest, there is one more thought worth carrying with you into sleep. It concerns the relationship between the Planck length and the existence of the universe as a place where complex things can happen, where atoms and molecules and stars and planets and living things can exist. The Planck length is determined by 3 constants of nature: the gravitational constant, Planck's constant, and the speed of light. These constants have the values they have, and as a result the Planck length has the value it has, about 10 to the negative 35 meters. Had these constants been different, the Planck length would be different, and the universe might be very different as well. If the gravitational constant were much larger, the Planck length would be much larger, and gravity would become important at much larger scales. A universe with a much larger gravitational constant would be one in which the quantum gravity regime was accessible at much lower energies, but also one in which gravity was much stronger, in which stars burned out much more quickly, in which planets could not form stable orbits, in which the universe might collapse back on itself before any complex structure could develop. If Planck's constant were much smaller, the quantum behavior of matter would manifest at much smaller scales, and the atoms that make chemistry possible would be much smaller, or perhaps unstable, since the uncertainty principle is what prevents electrons from collapsing into nuclei. A universe with a much smaller Planck's constant might not have stable atoms at all. The values of the fundamental constants, including those that determine the Planck length, appear to be finely tuned in ways that permit the existence of complex structure. This is the anthropic observation. We live in a universe where the constants have the values needed for our existence, because if they had values incompatible with our existence, we would not be here to observe them. Whether this fine-tuning reflects deep physical principles that we have not yet discovered, or the existence of a vast ensemble of universes with different constants of which we inhabit one compatible with life, or something else entirely, is one of the great open questions in physics and cosmology. The Planck length, determined by three fundamental constants, sits at the intersection of these questions. You are made of matter that exists at scales 14 to 15 orders of magnitude above the Planck length. Your atoms have size of about 1 angstrom, 10 to the negative 10 meters. The Planck length is 10 to the negative 35 meters. The ratio is 10 to the 25, 100 trillion. You exist at scales where spacetime is smooth and continuous, and the laws of physics, as we know them, apply with perfect reliability. The granular quantum foam of the Planck scale is unimaginably far below the level of your atoms, and yet that scale is where the laws that govern your atoms ultimately come from. The quantum mechanical rules that determine atomic structure, the gravitational constant that determines the strength of the force holding you to the Earth, the speed of light that sets the scale of electromagnetic interactions, all of them are encoded in the three constants that define the Planck length. The Planck scale is the foundation on which the familiar world is built, invisible from our height, but supporting everything above it. Rest in that thought. The foundation is there, even though you cannot see it. The laws are consistent, even at the scales you cannot probe. The universe is deep, but it is lawful. And tonight, in this quiet moment, you are resting on a foundation that extends all the way down to the smallest possible scale of space and time, solid and reliable and patient, holding everything together. There is something worth pausing over in the character of the two arguments that both lead to the Planck length, the black hole argument and the generalized uncertainty principle argument. They are not merely different mathematical routes to the same answer. They represent two fundamentally different ways of thinking about what limits our ability to probe the small, and the fact that they agree is a deep and meaningful coincidence. The black hole argument is, at its heart, an argument about energy and gravity. It says, to probe small scales, concentrate energy, but concentrated energy creates gravity. Enough gravity creates a black hole. A black hole hides what is inside. Therefore, there is a smallest scale you can probe. The argument is essentially classical in its picture of what a black hole does. It draws on Einstein's general relativity, on the Schwarzschild radius, on the event horizon as a barrier to information escape. The quantum part enters only through the de Broglie relation that connects the probing energy to the probing scale. The generalized uncertainty principle argument is, at its heart, an argument about measurement and disturbance. It says, to measure position, use a probe. The probe disturbs what it measures. At high enough energy, the gravitational disturbance from the probe adds to the quantum disturbance. The two effects combine to create a minimum total uncertainty in position. That minimum uncertainty is the Planck length. The argument is quantum mechanical in its picture of what measurement involves. It draws on the Heisenberg uncertainty principle, on the wave-particle duality of the probe, on the unavoidable disturbance that any measurement creates. These two arguments approach the Planck length from opposite directions, one from gravity and black holes, one from quantum mechanics and measurement, and arrive at the same answer. This convergence is a strong hint that the Planck length is not an artifact of either theoretical framework, but a genuine feature of physical reality, something that would be present in any correct unified theory, and that is being glimpsed from two different angles by our current incomplete theories. In physics, when two independent arguments lead to the same conclusion, it is usually a sign that something deep is being touched. The prediction of the positron from Dirac's relativistic wave equation, confirmed by its experimental discovery, was such a sign. The prediction of gravitational waves from general relativity, confirmed by the LIGO detections, was such a sign. The convergence of the black hole argument and the generalized uncertainty principle argument on the Planck length is, in the same spirit, a sign not yet confirmed experimentally and perhaps not confirmable by direct experiment in any foreseeable future, but meaningful nonetheless. The philosopher of physics, John Bell, who spent much of his career examining the foundations of quantum mechanics, once said that the most important question in physics was not any of the specific questions about particles or forces or fields, but the question of what quantum mechanics was about, what physical reality the mathematical formalism was describing. Bell's inequalities, which he derived in 1964 and which have since been experimentally tested many times, showed that quantum mechanics could not be completed by any local hidden variable theory, that whatever quantum mechanics was describing, it was not a system of particles with definite but unknown properties behaving according to local classical laws. The Planck length raises a similar question at a deeper level. What is spacetime about at the Planck scale? Is it a continuous manifold, as classical physics assumes, that simply cannot be probed below a certain scale for practical reasons? Or is it something genuinely granular, built of discrete pieces, a quantum foam whose structure is as real as the quantum structure of matter, but whose pieces are simply too small for any currently foreseeable instrument to resolve? The answer, when it comes, will likely come from theoretical physics rather than direct experiment. It will come from the development of a consistent and complete theory of quantum gravity, a theory that correctly describes the Planck scale from first principles, makes definite predictions about the large-scale universe that can be tested, and connects smoothly to general relativity and quantum mechanics as limiting cases in the appropriate regimes. Both string theory and loop quantum gravity have made progress toward this goal, and both have made partial contact with known physics. String theory has generated insights into the thermodynamics of black holes, Hawking radiation, the Bekenstein-Hawking entropy, that provided some of the first quantitative tests of quantum gravity ideas. Loop quantum gravity has resolved the classical singularities of general relativity, the Big Bang singularity and black hole singularities, replacing them with finite density quantum states, avoiding the physical infinities that plague classical general relativity. But neither theory is complete. Neither has made a unique, falsifiable prediction that distinguishes it from the other and from all other possibilities. The final theory of quantum gravity has not yet been found. The Planck scale remains, for now, the edge of the map. Before the story closes completely, there is a connection worth drawing between the Planck length and something much more accessible, much more a part of daily experience, that illuminates why the Planck length matters even for those of us who will never work on quantum gravity. The Planck length matters because it is the scale at which our two most successful and most fundamental theories, quantum mechanics and general relativity, break down simultaneously. This breakdown is not merely a technical problem for theoretical physicists. It represents a gap in our understanding of nature at the most fundamental level. We do not know, in any complete sense, what space and time are made of at the deepest level. We do not know what the initial conditions of the universe were. We do not know whether the universe has a finite or infinite number of degrees of freedom. We do not know whether spacetime is ultimately continuous or discrete. These are not abstract questions. They are questions about the foundation of everything, about the nature of the reality in which we exist, the reality of which we are made, the reality that produces the atoms and the forces and the laws that govern everything from the smallest quantum to the largest galaxy. And the Planck length is where these questions become unavoidable. Below the Planck scale, our current understanding fails. The failure is not partial or approximate, it is complete. The mathematical frameworks that have guided physics for a century and that have produced the most precisely verified predictions in the history of science cannot be consistently applied below the Planck length. Something new is needed. The search for that something new is the frontier of physics. And it is a frontier worth caring about, not because the Planck scale affects our daily lives in any direct way, but because the answers, when they come, will transform our understanding of what space and time fundamentally are. They will complete the picture that Newton and Maxwell and Einstein and Bohr and Heisenberg began to draw, the picture of a universe governed by deep and elegant laws, a universe that rewards patient and rigorous inquiry with glimpses of truths more profound and more beautiful than anyone had previously imagined. We are at the edge of the deepest question, and that is an extraordinary place to be. As the final quiet settles, consider the journey this story has taken you on. From the simplest act, opening your eyes to see the world through the physics of light and wavelength and resolution, through the history of microscopes and accelerators and the successive revelation of smaller and smaller structures in matter, to the point where the very logic of resolution turns against itself and generates, from the laws of physics themselves, a smallest possible scale. The Planck length is not a wall. It is a horizon, a point beyond which our current maps do not reach, but which tells us clearly that there is more beyond. The horizon is not the edge of the world, it is the edge of what we can currently see. And the history of physics is the history of pushing horizons back, of finding that what seemed like the edge of the world was merely the edge of our current instruments and our current understanding. The Planck length is, at present, a horizon we cannot see beyond, but we can see it clearly from here. We can see its outline, measure its distance, calculate its value, understand why it is there and what it means. And in seeing it clearly, we have already learned something extraordinary, that space and time, the most fundamental framework of our experience, have a smallest meaningful scale, a grain, a limit to their divisibility. That limit is very, very small. And you lying here in the dark are very, very far above it, made of atoms whose size is many orders of magnitude above the Planck scale, resting on a planet whose gravity is gentle and classical, breathing air whose molecules are quantum mechanical, but whose quantum nature is invisible at the scale of breathing. The Planck scale is the foundation you rest on, invisible and silent, holding everything together at scales too small for any instrument to resolve. And it will be there tomorrow and the day after, and for all the time to come, patient and exact and fundamental, waiting to be understood. That is enough. That is more than enough. Rest now. Richard Feynman, the physicist who did more than almost anyone to develop quantum electrodynamics into a complete and calculable theory, was famous for his ability to explain complex physics in clear and vivid language. He once said that if you think you understand quantum mechanics, you don't understand quantum mechanics. By this, he meant not that quantum mechanics was beyond understanding, but that the intuitions we bring to it from everyday experience are systematically misleading, that the quantum world is genuinely different from the classical world in ways that resist easy analogies and comfortable pictures. The Planck length represents a place where this difficulty becomes absolute. We have reasonable intuitions about quantum mechanics, developed through decades of working with its formalism and comparing its predictions with experiment. We have reasonable intuitions about general relativity, built up through the study of black holes and gravitational waves and the large-scale structure of the universe. But we have no intuitions at all about what happens at the Planck scale, where both theories simultaneously apply and simultaneously fail. We have never observed a system at that scale. We have no experimental guidance. We have only mathematics, and the mathematics is not yet complete. This is both a challenge and an opportunity. The challenge is to develop the theoretical framework of quantum gravity without the experimental guidance that has always been essential to progress in physics. Every previous advance in fundamental physics has been driven by the interplay between theory and experiment, theory suggesting new phenomena, experiment confirming or refuting the suggestions, theory revising itself in response. At the Planck scale, this interplay is largely absent, at least in the direct form we are accustomed to. Theorists must navigate by other lights, mathematical consistency, the reproduction of known physics in appropriate limits, the convergence of different theoretical approaches on the same answers. The opportunity is that the question itself is so fundamental and so precise that any correct answer will have implications far beyond quantum gravity. A correct theory of quantum gravity will be a theory of everything, in the sense that it will encompass all the known physics and provide the foundation on which everything else rests. It will explain not just the Planck scale, but the large-scale structure of spacetime that general relativity describes, and the quantum behavior of matter and fields that quantum mechanics describes. It will be the deepest and most complete description of physical reality that physics has ever achieved. Whether that theory is string theory, or loop quantum gravity, or something entirely different that has not yet been conceived, no one knows. What we know is that it must exist, that the universe is governed by consistent laws, and that a consistent description of those laws at the Planck scale must be possible, even if we have not yet found it. The search continues. The frontier is real, and the Planck length, tiny and precise and profound, marks the edge where the search becomes most urgent and most difficult and most rewarding. You have traveled a long way tonight, from the act of seeing to the smallest possible scale of space. From optical microscopes to electron microscopes to particle accelerators to the theoretical frontier of quantum gravity. From visible light to X-rays to the de Broglie matter waves of high-energy particles. From atoms to nuclei to quarks to the edge, where probing further creates black holes. The Planck length is that edge, 10 to the negative 35 meters, the scale where quantum mechanics and gravity meet, and neither can be applied without the other. The scale where the smooth spacetime of classical physics gives way to something granular and uncertain and not yet fully understood. The scale where distance, in any operationally meaningful sense, ceases to exist. It is the smallest answer to the largest question: how deep does the universe go? And the answer is, to the Planck length, and then into territory that our current maps cannot describe. That is a remarkable answer, not a disappointment but an invitation, not a wall but a horizon. Not the end of the story, but the beginning of the next chapter, a chapter that physicists are even now beginning to write, with mathematics and insight and the patient willingness to follow ideas wherever they laid. The night is complete around you. The story has found its resting place. And you can rest too, knowing that the universe has a foundation, that the foundation is deep and ancient and extraordinarily small, and that human minds have found their way to the edge of it and stood there, looking out at the unknown, curious and unafraid. Sleep well. The Planck scale will be there in the morning, unchanged and exact, holding everything together at the bottom of the world. As we come to the end of our journey tonight, the story can begin to settle around you. We have traveled from the act of seeing with our own eyes, through the history of microscopes and particle accelerators, through the logic of resolution and the energy wavelength relationship, to the moment where that logic turns on itself and creates a black hole. We have seen the Planck length emerge from the physics of black holes and from the generalized uncertainty principle, the same scale, from two different directions. We have glimpsed the two great programs of quantum gravity, string theory and loop quantum gravity, each offering its own picture of what space might be at the deepest level. There is no need to hold any of that tightly now. You can let the details soften into impressions, the image of light scattering from an object and carrying information to your eye. The image of a particle accelerator bending proton beams in a ring 27 kilometers around. The image of a black hole forming at the Planck scale, hiding the very thing you were trying to see. The image of spacetime foam, the wild, granular, uncertain texture of space at the most fundamental level we can identify. Let these images drift through your awareness and dissolve, like ripples on a dark pool, like the last light fading from the sky. The universe has a smallest scale. And you are made of matter that exists at scales billions of times larger than that smallest scale, large enough to be stable, large enough to be complex, large enough to form the atoms and molecules and cells and thoughts that constitute a human being lying still in the dark, breathing slowly, drifting towards sleep. You are, in the most literal physical sense, far above the Planck scale. You exist in the realm where spacetime is smooth and continuous, and the laws of physics, as we know them, apply with perfect reliability. The quantum foam is far below you. The granular spacetime is far below you. You float, in a sense, on the surface of a deep and largely unexplored ocean, the ocean of Planck-scale physics, and the surface is calm, and the night is quiet, and there is nothing you need to do but rest. Let your breathing slow, let your body settle into wherever it is. The universe will keep unfolding on its own, just as it always has, steady, patient, and kind. Sleep well, good night, still drifting. Let the rain take over from here. Close your eyes and let it wash everything away.